Hello, everyone. Today we are going to go over the question on the practice exam 3. So let's start with the first question. We want to calculate the double integral over a rectangular region. X is from 0 to 1, y is from -2 to 2. So we can set up this way here. Uh, X is from 0 to 1, y is from -2 to 2, and we have x times y squared over x squared plus 1 dy first and then dx. If we write the interval this way here, then we'll do dy first and then dx. And for this integral, as you can see here, first, this is the rectangular region, okay? So all the bands, they are constant. Second, if you look at the integrand here, as you can see, this is the product of two functions. One depends on x, and the other one depends on y. Okay, so this is the special case we mentioned in the lecture. We can write this as a product of two single integral. So we'll have 0 to 1, x over x squared plus 1 dx. And the other one is -2 to 2, y squared dy. Okay, so we can split into two integrals here. One depends on x, the other one depends on y. And for each one, it's not that bad to find the to um to find the antiderivative and evaluate the integral here. For the first one, we're going to use u substitution. So if you let u equal to x squared plus 1, then this one, the antiderivative is 1/2 ln, and x is from 0 to 1. And for the second one is 1/3 y cubed from -2 to 2. Okay, so now you just need to plug in. We'll have 1/2 ln2 minus 1/2 ln1. And here, when we plug in, we're going to get 1/3 minus -1/3. And we know ln1 is 0. So the first one gives us 1/2 ln2. And the second one here, when we subtract these two numbers, we're going to get 16 over 3. So multiply these two numbers together, we got 1/3 ln2. So this is the final answer here, okay? So the correct choice is the first one here, 1/3 ln2 for the first question, all right? And the second question, we want to identify the surface. And as you can see, when we say the surface, that means this is in 3D, okay? And now we have rho equal to 4 cosecant phi. And since if you look at the conversion from rectangular coordinate to spherical coordinate, we don't use this cosecant phi here. So we're going to convert cosecant to 1 over sine. Okay, so on the right hand side here, we can write this as 4 over sine phi. So let's multiply sine phi from, on both sides here. So we're going to get rho sine phi equal to 4. So now let's look at the left hand side here. What's rho sine phi? Rho sine phi is r, right? Rho cosine phi is z. Rho sine phi is r. And r is square root of x squared plus y squared. So we can write this as x squared plus y squared equal to 16. But remember, we said this is a surface, so x squared plus y squared is not a circle, okay? Circle, this is in 2D, all right? We consider in 3D here, we're going to get a cylinder. Okay, so this gives us a cylinder here. So this is the second question. Let's, let's move on. The next one, it gives us the point P in the rectangular coordinate. So this is X, Y, Z here, okay? And which of the following is correct? First, it says the point P is on the surface R equal to 1. So if you remember, R is square root of X squared plus Y squared. So let's plug in the X and the Y value. X equal -1 and Y equal to 0. So yes, we do get R equal 1 here. So the point P is on the cylinder, R equal to 1. So P is correct. The second one, it says the point P is on the surface, theta equal to pi over 2. So whenever you look at theta, you only need X and Y. Okay, so that kind of like just like if you consider in 2D, just in the polar coordinates. Okay, you don't need Z to determine the angle theta. Okay, so we just need to look at the X and the Y here. So in 2D, let's plug the point. X equal minus 1, Y equal 0 is right here on the x-axis here. So can anyone tell me what's the angle here? This angle is the angle theta, and you can see the angle is pi. Okay, so it's not pi over 2. Okay, so this is not correct. If it's a pi over 2, it would be like on the positive y-axis here. Okay, that would be pi over 2. Okay, so Q is not correct. And next, we're going to move on to the R. The point P is on the surface, phi equal to pi over 4. So the angle phi, we have the angle phi, we can use the formula in the conversion from spherical to rectangular coordinate. Cosine phi, we can write as z over rho here. And z is 1. And rho is square root of x squared, y squared, z squared. We sum them up. Okay, so we have 1 plus 0 plus 1. So that gives us 1 over square root 2. Cosine phi equal to 1 over square root 2, or you can say this is square root 2 over 2 if you rationalize it. So the angle phi indeed is pi over 4 here. Okay, cosine pi over 4, it gives us 1 over square root 2. So R is correct. Both P and R, they are the correct statement here. Okay, so this is question number 3. Any question? Let's move on. The next one.
I have a question. For the previous question on why couldn't we use tangent data as equal to y over x to find things?
Okay, your voice is kind of breaking. I cannot hear you clearly. Can you repeat your question?
Hi, can you hear me now?
Yes.
So, why can't we use tangent theta is equal to y over x to find what theta is in this case?
Oh yeah, sure. You can use that.
But then it'll give us 0, right?
So tangent theta is y over x, right?
Yes.
So that gives us 0. So when tangent theta equals 0?
Oh, okay. Yes, it's equal to when 2 pi or pi.
It's 0 or pi, right?
Yes.
Okay, but as you can see here, if it's 0, that would be on the positive x-axis, right?
Yes.
But the point here, x equal minus 1, so it's on the negative x-axis. So we're going to choose theta equal pi in this case. But anyway, it's not pi over 2. Okay, tangent pi over 2 is not defined. Is that good?
Yes.
Okay.
Thank you.
Let's move on to question number 4. Question number 4. P is the triangular region in the xy plane with vertices 0, 0, 1, 1, 2, 0 here. So let's draw a picture for this triangular region. The origin 0, 0, the point 1, 1, and the point on the x-axis 2, 0. So this is the region D. Okay. Okay, so this is the region D. And we want to write this double integral as an iterated integral here. And as you can see, if we look at the choices here, there's some of them written in the order dx dy, and some of them written in the order dy dx. So first, we want to determine, we want to do dx dy or dy dx. So if we want to do dx dy, then we're going to draw a line in the x direction. So we're going to draw a line in the x direction. So you can see the left function is always the same. The right function is the same. So dx dy is good. Okay. And let's take a look on the dy dx. Is this integral in this order? Is this good? If we want to do dy dx, let's draw a triangle again. If we want to do dy dx, that means we're going to draw a line in the y direction. And there's an issue here. When we draw a vertical line, can you see that? The top function is not always the same. You see that? Okay, so the top function is not always the same. So if you want to do dy dx, you need to write as two integrals here. First one, you can see the left triangle, the top function is the same, and the other half, the top function is the same. So if you want to write dy dx, we are not able to write as only one iterated integral. Is that good? So first, we are determining the order. So in this case, we want to do dx dy, and we can write as just one iterated integral here. Okay, so this is the order we want to use, dx dy. So now we need to determine what's the function here. So the line is passing through the origin 0, 0, 1, 1. So this is the equation y equal x. And the other line here on the right, it passes through the point 1, 1 and 2, 0. So the slope is -1. And okay, so it's y equal minus x plus 2. Okay, you determine the slope and use one of the point to determine the intercept here. Okay. Are you okay with the two-line equation we got here? So now we want to find the bands for dx here. So it's from the log function, and since we want to do dx, so we want to write x in terms of y. So x equal y. That's the lower band. X equal y. So in fact, this is the answer here. X equal y, and the upper band here, x equal minus y plus 2, or 2 minus y. So this is the upper band, okay? And for this one, it's not correct. The first one is not correct, okay? And the bands for y, so you can see the bands for y here is between two horizontal lines. So this is y equal 0, this is y equal 1. So that's the bands for the outer integral, okay? So this is question number 4. Is that good? And next, question number 5. Question number 5. The function f is continuous function. How many of the following statements are true here? So the first one, it says, we have a rectangular region. Y is from C to D, and X is from A to B. And now you can see the order here is the same. However, the interval, they are switched. Is this correct? When we switch the interval, we need to also switch the change the order from dx from dy dx to dx dy here, because the interval corresponding to the x interval is from A to B, as you can see, and the interval corresponding to the y interval is from C to D. So the first one is not correct. We need to change the order of integration on the right-hand side here, okay? And for the second one here, this is now rectangular region. Y is from 0 to x, and x is from 0 to 1. So y is from 0 to x. So this is y equal x. Y is from 0 to x, and x is from 0 to 1. So this is the region here, because y is from the base until it touched the line y equal x. So we draw a line in the y direction here when we integrate with respect to y first. Okay, so this is the region. Now let's look at the right-hand side here. When we change the order, do we have this interval? Okay, so let's take a look. So this is the line y equal x. And now let's take a look. It said x is from 0 to y. X is from 0 to y. So x is, you need to draw a line in the x direction. X is from 0. That's the left function until it touch the right function. And y is from 0 to 1. So as you can see, these two are different two regions here. Okay, therefore, they are not the same. Okay, you need to have the same region. Okay. And the third one here, we have a rectangular region. Y is from 0 to 2, x is from 0 to 1. The integrand is e to the power x plus y. Can we write this as a product of two single integral? We mentioned that if it's a rectangular region, and if the integrand can be written as the product of two functions, in this case, we can write this as ex times ey. One depends on x, the other one depends on y, then yes, we can split this into two single integrals. Okay, so this one is correct. The third one is correct. And the next one, the integral, double integral over the region D, dA, it presents the area of the region. Is this correct? So you can see there's nothing for the integrand, which is 1. So that means we just add in each tiny area together. If you use the concept for the Riemann sum over the region D, then in D, it gives us the area of the region. Okay, so this is correct here. And the next one, the integral, the double integral over the region D, f of x, y, dA, is the volume of the solid that lies between the surface and the region D on the xy plane. Is this correct? Okay, then it really depends on the surface. Where is the surface? If the surface is above the xy plane, like here, then yes. Okay, so that presents the volume. If z equal to f of xy is above the xy plane, then it's the volume. But it doesn't tell us if z is always positive. So it may be something like this. This is the region D here on the xy plane, and the surface is down here. So now when you find the volume between the surface and the region D on the xy plane, then this one, it won't give us a positive number, okay? So in order to get the volume, you need to put the absolute value here. Okay, you need to put the absolute value here. So that way the height will be always positive, okay? Or in this case, you can see the upper surface is 0, that's on the xy plane, minus the lower surface, okay? So you're going to have the region D, the upper surface minus the lower surface, dA. So in this case here, in fact, it's not f of xy, it's minus f of xy give us the volume, okay? So in the question here, it doesn't tell us the function f is always positive, okay? So this one is not correct here, okay? So for this question, only the third one and the fourth one, those two are correct. So two of them are correct here. Is that good? All right. And the fourth one is correct. This is just the definition, okay? Just like the definition for the volume, it can be written as the triple integral 1 dV. So this is the volume of the solid region E. And the area of the region D, this is the definition. We can always write it this way, okay? The last one is not correct because we don't know if z is always greater or equal to 0, okay? You already tell us the function is continuous in the beginning here, all right? But it doesn't tell us if z is always above the xy plane because here you tell us this double integral present the volume between the surface and the the region on the XY plane, but as you can see, I draw another picture here. The surface Z can be below the XY plane, less than 0. Okay, so in this case, the volume need to be written in this way. As you can see, there's a minus sign here. Okay. Okay, so if like this type of question, when we test your concept, true false question, then if it doesn't say F is positive, then you cannot assume it's positive. Okay, so in this case, this is wrong. Okay, the last one is wrong. Okay, the next one, question number 6. We have a triple integral here, and E is a solid between the sphere, two spheres here, one with radius 1, the other one with radius 2. And we're going to write the integral in spherical coordinate. So the first sphere, we can write this as a rho equal 1. The second one, we can write this as a rho equal 2. Okay. Therefore, you can see when we do the conversion here, rho is from 1 to 2 because the region E is between two spheres. Okay, it's from 1 to 2. But say it's in the first octant. So if it's in the first octant, when we do the projection onto the XY plane, you're going to have this region here, right? When you project the whole thing onto the XY plane, you're going to have this region. Therefore, theta is from 0 to power 2, okay? And phi is from 0 to power 2. The reason is, so you can see we have two spheres here, okay? We have two, but we only consider the first octant, okay? So that means phi starting from 0 until it touch the XY plane. So this is a right angle here. So this is phi equal to pi over 2 because we only consider the first octant. So phi is from 0 to pi over 2. But for this question, they already give us the bands, okay? But you should know how to get the bands here, okay? And now for this question, it only asks us the integrand. So it's not that bad here. You just need to convert everything in terms of rho, phi, and theta, okay? So Z is rho cosine phi. But is that the answer for the integrand F, rho cosine phi?
No, you need to include the Jacobian rho
Yes.
squared sine phi.
When we convert to the spherical coordinate, you need to multiply by the absolute value of the Jacobian, which is rho squared sine phi here. Okay, rho squared sine phi. So together, this will give us the integrand F. Okay, so we have a rho q sine phi cosine phi, the last one here. Okay, is that good? And let's look at question 7. Question 7, we want to find the volume inside the sphere, outside the cylinder. So we have a sphere here with radius 5. The cylinder is smaller, radius 3. Okay, so we have something like this. Okay, so this is a cylinder. And we want to find the volume inside the sphere, outside the cylinder. So this is the part we want to find the volume here. So when we project the whole thing onto the XY plane, we are going to get the region like this, a donut-shaped region, because we need to take out the cylinder. So the inner one radius 3, the outer one, the radius 5. Okay, so this is the projection on to the XY plane. So now to find the volume, if you use double integral here, R is from 3 to 5. We're going to use polar coordinates, by the way, okay? 3 to 5. And theta is from 0 to 2 pi. If we use double integral, then the integrand should be the upper surface minus the lower surface, right? Okay, is the upper surface minus the lower surface. So you can see Z is changing from the bottom hemisphere to the top hemisphere. Okay, so this is z equal to square root of 25 minus x squared minus y squared, but with the minus sign in the front. That's the bottom hemisphere, and this is the top. Okay, so we'll have square root of 25 minus r squared minus the lower surface. And when we use the polar coordinate, we have r d theta. Do not forget the Jacobian here. Okay, and some of you probably will use the symmetry. You say, I just want to find the volume above the xy plane, and then I multiply by 2. That also work. Okay, so you can see, in fact, when you use the upper surface minus the lower surface, this is twice of square root. Okay, so if you want to use the symmetry, you can use 2 times the square root. And here I set up using the double integral. Can we use the triple integral? Yes, you sure can. Okay, so if you use the triple integral, then that would be r dz dr d theta. It's using the cylindrical coordinate here would be easier. And z is from the bottom hemisphere to the top hemisphere. Okay, r is still from 3 to 5, theta is from 0 to 2 pi. And you can see, in fact, when you evaluate this integral, the inner one, it will give you this integral, the double integral. So they are equivalent, okay? They are equivalent. So it doesn't matter if you want to use the double integral or the triple integral here. Is that good? All right. So either will be fine, okay? So after you evaluate the inner integral, that gives us the double integral like this, okay? So we want to do the calculation here for the integration. So we have 0 to 2 pi, 3 to 5, and we have r, 2r times square root of 25 minus r squared dr d theta. Okay, and how we're going to evaluate this integral here?
Use substitution.
Yes, we use u substitution, u equal 25 minus r squared. So remember for the exam, the integration technique, you need to know the u substitution, integration by parts, and also the trig integral for sine, cosine type, okay? So be sure if you forget some of them, you need to go back to review that, okay? So when you use u equal to 25 minus r squared, then you will get something like this. Okay, so this will give us, this is u here, square root u, and du equal minus 2r dr. So this part here is just minus du. Okay, so when you find the antiderivative, you're going to get u to the power of 3/2. And I'm going to change back to r to skip a step here. And then I'm going to divide 3/2. So I'm going to have minus 2/3 here. And r is from 3 to 5. Is that good? And now you can just plug in the upper limit minus the lower limit. Okay. So what do we have here? When we plug in the upper limit, you're going to get 0 because 25 minus 25, that's 0. And when we plug in 3, we are going to get 25 minus 16, sorry, 9, you got 16, okay? And 16 to the power 3/2, what's 16 to the power 3/2? You take the square root first, so you got 4. And what's 4 cubed? We just leave it as 4 cubed for now, okay? So you're going to get 2/3 times 4 cubed. The reason we want to leave it as 4 cubed because as you can see, the final answer is written in this way, okay? So I'm going to just leave it as 4 cubed here. So the inner part here, it gives us 2/3 times 4 cubed. And now we're going to integrate with respect to theta, and this is just a number. So the final answer is just 2 pi times the number we have here. So together here, we can see there's another 4 here. Do you see that? Okay, there's another factor of 4. So together we have 4 to the power 4 times pi over 3. So that's the final answer. Okay, 4 to the power 4 pi over 3. Therefore, in this case, n equal to 4. N equal to 4. Is that good? This is the final answer here after we evaluate. Okay. So this is question 7. Question number 8. Question number 8, we want to find the volume of the part of the solid ball rho is less than or equal to 1 lies between two cones. So we have a unit sphere and we have two cones. One is power 3. So this is the cone pointing up. And where is the angle phi equal 2 power 3? We know phi equal power 2 is the xy plane, right? Phi equal power 2 is xy plane. And 2 power 3 is larger than power 2, so it's below the xy plane, down here. So this is another cone down here, 2 power 3. And we want to find the volume inside the unit sphere between the two cones. So that would be this part here. This is the volume we want to find here. So when we project the whole thing onto the xy plane, we're going to get a unit circle. This is the unit circle here, okay? And the volume, we can, because it involved the unit ball here, so it would be easier to use the spherical coordinate, since also we the equation it gives us here, the cone, you can see it's given in the spherical coordinate. So let's use spherical coordinate here. So we have a rho.
Professor Wang,
Yes.
um, how did you know where to put the phi equals 2 pi over 3?
Okay. So earlier I mentioned that phi equal power 2. What's phi equal power 2? Can anyone tell me? Phi equal power 2, that gives us the xy plane, right? Which is z equals 0, okay? Phi equal power 2, that gives us the xy plane. That's a 90 degree away from the z axis, right? Okay, and 2 power 3, this is larger than power 2, so you need to keep going down. You'll go down below the xy plane. So it would be below the xy plane like this. So the cone is down here, below the xy plane. Is that good?
Yeah, thank you.
All right. So now we need to set up the integral here because it's inside the sphere. So rho, as you can see, when you draw a ray here, is from 0 to 1. And the angle phi, as you can see, is between two cones. So it's from power 3 to 2 power 3. And theta, you're going to look at the projection on the xy plane that give us the bounds for theta is from 0 to 2 pi. Is that good? Okay, so this is how we set up the volume for the solid we have here. Okay, and now once we have this, you can see that all the bounds here, they are constant, and the integral is rho square times sine phi. So can we split this into 3 single integrals? Can we do that?
Yes.
And it would be easier, okay? So if you don't want to do it this way, that's totally fine, okay? You just need to calculate from evaluate the integral from inside out, okay? So now we have something like this, okay? So for the theta, there's no integrand here, that means 1. And the integral is just the length of the interval, which is 2 pi. And for this one, you're going to get minus cosine phi. Phi is from power 3 to 2 pi over 3. And the last one is rho square over 2 is from 0 to 1. So hold on. That's a rho square here. Rho square here. So that's rho cube over 3. Okay. The square was missing earlier. Okay. So this one gives us 1/3. Okay. So you can just evaluate the integral here. And this part here, when you plug in, you're going to get 1. Okay. This part here, you're going to get 1. And this gives us 1/3. So you multiply all of them together, you're going to get 2 pi over 3. The final answer is 2 pi over 3 here. Okay. Is that good? Okay, so this is question number 8. And next, question number 9. We want to write the equation in rectangular coordinate here. And we have rho equal to 4 sine phi sine theta. All right, so first, in order to change to the rectangular coordinate here, we need to multiply rho on both sides. Okay, so we have rho squared equal to 4 rho sine phi sine theta. Rho squared is x squared plus y squared plus z squared. And can anyone tell me what's the right hand side? What's the rho sine phi sine theta?
Y.
That gives us y. So when we have x squared plus y squared plus z squared equal to 4y, what do we have? This presents a sphere, and the center is on the y-axis. Okay, so you're going to get, you can complete the square for y. Okay, move the 4y to the left and add 4 to both sides here. So you're going to get x squared plus y minus 2 squared plus z squared equal to 4. Okay, so this is the sphere we want. Okay, and this one is the cylinder, and that can be written as r squared. Okay, and r is rho squared sine phi. So in fact, this can be written as rho sine phi equal to the last one.
Oh my God.
And
Sailor.
the fourth one,
Baby, come here.
Oh, my goodness.
could you please
What did
mute,
she get
mute
into?
yourself? Sorry, I'm going to mute everybody.
You don't get that. You get to be with me.
Okay. All right. So for this one, x squared, y squared, z squared equal to 4. This is the this is a sphere center at the origin. So this is a rho equal to. Okay. And this one is the horizontal plane. This can be written as rho equal to, if you want to write as the spherical coordinate, z equal 4. This can be written as rho cosine phi equal 4, so rho equal to 4 secant phi. Okay, and for this one, the center is on the z-axis. We have seen this many times in class. So can anyone tell me what's the equation? Rho equal to anyone? X squared, y squared, z minus 2 squared. Yes, rho equal to 4 cosine phi. Okay, now you can see for this too. The one given here, rho equal to 4 sine phi sine theta, and this gives us the sphere on the y-axis, and this is the sphere on the x-axis. So can anyone quickly tell me what's the answer? What's the equation here? Rho equal to, it's very similar to this one, but you can see this is 4, this gives us 4y here, but this one, it need to give us 4x, so it should be 4 sine
Phi cos theta.
Yes, cosine theta. Okay, so now for each of the choices here, we have the corresponding equation in the spherical coordinate here. Okay, all right. So be sure you practice different type. Okay, because you really don't know which one you're going to get on the test. Okay, so even though we put this on the practice exam, but as you can see on the test, there's different versions. So the one you got probably different than the one I have. Okay, so each of you have different versions, so you need to practice different type of equation like this. Okay, so this is question number 9. And next, question number 10. Question number 10, we want to find the volume above the cone, below the sphere. Okay, so let's draw the solid first. This one also a very common one we have seen. Okay, inside the sphere, below the sphere, and above the cone. So it's the ice cream ship region here. Okay, so this is the region we consider, and the cone, it has the equation z equal to square root of x squared plus y squared. And the sphere has the equation x squared y squared z squared equal to 4. Okay. All right. And now it says the volume. So this is using the double integral, as you can see, and in the polar coordinate here. So as you can see here, this present dA, and this part here should be the upper surface minus the lower surface. And you can see the upper surface is from the upper surface is from the sphere, which is square root of 4 minus r squared. The lower surface is from the cone, which is r. Okay, so this can be written as z equal r, and the upper surface that you can solve for z, which is square root of 4 minus r squared. So that's why we use the sphere, the upper surface minus the lower surface. And now we want to write down the bands for the data here. So we're going to do the projection onto the XY plane. You're going to get a circle. So this is the projection on the XY plane. But now the question is, as you can see here, we know it's a circle, okay, but we need to find the upper bound for R. What's B here? So we need to determine what's the size of the circle here. So the size of the circle, as you can see, is come from the intersection here. This is the intersection of the cone and the sphere. So we're going to find the intersection. The intersection, we're going to set an equal. So we have x squared plus y squared, and z is the square root. So we have x squared plus y squared. When we square that, the square root disappear, set that equal to 4. Okay, so this is how we find the intersection. So now we have 2x squared plus 2y squared equal to 4, x squared plus y squared equal to 2. Therefore, that tells us for this circle, the radius is root 2. The radius is root 2. So the upper bound, this is r equal to square root 2. The upper bound for r is square root 2 here. Is that good? And this technique we've been using, okay, when we do the projection onto the XY plane, and to find the size of the circle, you always look for the intersection, okay? We always look for the intersection. Is that good? And let's look at question 11. Question 11, it gives us a double integral, but we are not able to evaluate this integral directly. When we integrate with respect to y first, as you can see, sine of y cubed, there's no way we can find the integral. So we're going to change the order of integration. But before we do that, we need to figure out what's the region we consider here. And it tells us x is from 0 to 1, and y is from x squared to y equal 1. So we're going to draw the region first. This is y equal to x squared, and this is y equal 1. And y in the y direction, so we draw the line in the y direction here, is from the parabola until it touched the horizontal line, okay? So but x is from 0 to 1, from 0 to 1, so only the right side here, okay, not the entire region enclosed by the line and the parabola, only the right side, okay? So this is the region. Now we're going to change the order here. So we have x cubed sine y cubed. We're going to do dx first and then dy. When we do dx first, we're going to draw a line in the x direction. Okay, so now we're going to draw a line in the x direction. The left function is 0. The right function is the parabola, but now we want to write x in terms of y, so x equal to square root y. Everybody okay with the bands we have here for x? Now y is between two lines, horizontal line 0 and 1. So here we have the bands after we change the order of integration here. So for this one, it's a lot easier to do the integral. So we integrate with respect to x first. So sine y cube is just a number. So we're going to write sine y cube here, a number. We integrate x to the power 3. That gives us x power 4 over 4. And x is from 0 to square root y, dy. Now plug in the upper limit. When x equal to square root y, that gives us y squared. So we have y squared over 4 sine y cubed. Plug in x equals 0, that's just 0. Okay, so we'll have this. So now to evaluate this is much easier because we can use u substitution. U equal to y cubed. Okay, so we'll have du equal to 3y squared dy. Therefore, this part here can be written as sine u, and y squared dy is du over 3, and then again divided by 4, so that would be 1 over 12 du. Is that good? So this is the use substitution. So the antiderivative is minus cosine u, and now we're going to change it back to y. So u is y cubed. Now y is from 0 to 1. Now plug in the upper limit minus the lower limit. Plug in 1, you have a cosine 1, minus cosine 0, that's 1. Okay, and you can see because they put the 1 over 12 in the front, all positive number here, the coefficient in the front, all positive. So we're going to just put the minus sign inside here by switching the order. So you're going to get 1 over 12, 1 minus cosine 1. Okay, so this is the final answer. And we evaluate the integral by changing the order of integration here. Is that good? And next, we want to change the point from Cartesian coordinate, or sometimes we call the Cartesian coordinate, sometimes we call the rectangular coordinate to spherical coordinate here. So this is x, y, z, and we want to change to rho theta phi here. Okay. So rho is the distance, x squared, y squared, z squared. So we'll have 3 plus 1 plus z squared, that's 12. So that's 16. Root 16 is 4. Okay, so this is the first one. And theta, whenever we want to look at theta, we only look at x and the y. We mentioned that before. Okay, so on the xy plane, the point square root of 3 comma minus 1 is in quadrant 4. First, you need to locate the point first on the xy plane, okay? And you use tangent theta equal y over x, and you're going to get y over x. So you need to pick the angle in quadrant 4. Tangent theta equal to negative 1 over square root of 3. There's two angles, one in quadrant 2, the other one in quadrant 4. Okay, so in this case, you need to pick 11 pi over 6. Is that good? You don't want to pick 5 pi over 6. 5 pi over 6 is in quadrant 2. However, the given point on the xy plane is in quadrant 4. Okay, so this is the angle we're going to pick, 11 pi over 6. And next, we're going to find the angle phi. Angle phi, we're going to use the formula cosine phi equal to z over rho. Z is 2 root 3. Rho is 4, so we can reduce that to root 3 over 2. So the angle phi is pi over 6. Remember, the angle phi is always between 0 and pi. Okay, so here we choose pi over 6. So 4, 11 pi over 6, pi over 6. So that should be the answer here. All right. So this is question 12. And question 13, we want to find the Jacobian here. To find the Jacobian, from XYZ to RT theta. So we can set up a 3 by 3 determinant here. First, we use X, take the derivative with respect to R. So we got T cosine theta. Take the derivative with respect to T, we all have R cosine theta. Take the derivative with respect to theta, we have minus RT sine theta. Is that good? And now use Y, do the same thing here. We'll have T sine theta, R sine theta, RT cosine theta. Now use Z, we're going to take the derivative with respect to R. We got 2R. And since Z equal R squared, there's no variable T and theta. So when we take the derivative with respect to T and theta, we got both 0 here. Okay. And to calculate this 3 by 3 determinant, you can use the first row and the sign is alternating. Okay, so we'll have T cosine theta. And you can see, in fact, this one here, when you remove the first row and the first column, what do we have?
0.
That's 0, right? Times 0 minus R cosine theta. And what do we have here? 0 minus that, right? So we'll have negative 2R squared T cosine theta. Do you see that? One more time. This way, we got 0. Subtract this. That's 2R times RT cosine theta. So that's what we have here. And the last one, we have plus RT sine theta. And what do we have? This way is 0. And this way is 2R squared sine theta. So we have 0 minus 2R squared sine theta. The first one is 0. And now we still have two terms here. So let's simplify a little bit. So here we got positive sign here. I make a mistake here. Did anyone see that? The third one, we have a positive sign, but here we have a minus sign. So that should be minus RT sine theta. Okay. Okay. So I make a mistake. The third term here should be minus RT sine theta. All right. So here we have a positive sign. So we have 2R cubed T cosine square. Am I right? When we multiply this together, we got 2R cubed T cosine squared theta. And here, again, 2 minuses, that becomes positive. And we have 2R cubed times T, and this gives us sine squared theta. And this too, we have a common factor of 2R cubed T. We can take that out. Once we take that out, the remaining part is cosine squared plus sine squared. And that gives us 1 here. So the final answer of the Jacobian is 2R cubed times T. Okay? Is that good? This is question 13. Find the Jacobian. Okay, I just want to remind you, for the Jacobian is either the 2 by 2 determinant or the 3 by 3 determinant. Okay, so the determinant is not always positive. So if we want to get the find the Jacobian, it's possible to get a negative number. Is that good? It's possible to get a negative number. But when we do the change of variable in the integration, when we do the change variable of integration to, we change everything in terms of UV, for example, here, when you multiply the Jacobian, because Jacobian is not always positive, you need to add the absolute value when we do the integration. Okay, you need to add absolute value. But when you ask us to calculate the Jacobian, it's possible to have a number less than 0. Okay, so this is question 13. And how did you get the third determinant one more time? The third one here, the third term, you meant? Okay, so the third term, so you use this. So that's why we have this one here, minus RT sine theta. And we're going to remove the third column and the first row. So calculate this 2 by 2 determinant here. That gives us 0 minus 2r squared sine theta. 0 minus 2r squared sine theta. That's why we have this, negative 2r squared sine theta. Okay? So if the 2 by 2 determinant of 3 by 3 determinant here, you calculate whatever the calculation is, that's the Jacobian. So if this one somehow when you do the Jacobian, after you simplify, you get like minus 2r, then this is the answer, minus 2r. You'll keep the minus sign for the Jacobian. When they ask for the Jacobian, it can be a negative number. But when we do the integration, when we do the integration for the change of variable, you add the absolute value for the Jacobian. Okay? We only add absolute value when we do the change of variable for integration. Is that clear? And next, question 14. We want to find the volume bounded by the paraboloid. This is open downward. The vertex is at 0, 0, 8 here, open down. So this is the paraboloid. And the plane z equal 6. Z equals 6 is here. So this is z equals 6. So the volume bounded by the paraboloid and the plane. So this is the region we consider, but only in the first octant. So if in the first octant, when we do the projection onto the XY plane, that's only a quarter of a circle. Agree? Okay, only a quarter of a circle here. And now, to find the volume here, we mentioned that before, you can either use double integral, triple integral, okay? So if you use the double integral, and we want to use the polar coordinates here, okay? So you use the upper surface minus the lower surface. This is the upper surface minus the lower surface dA, and we're going to convert to the polar coordinates here, okay? And now we need to write down the bands for R. So how are we going to find the bands for R? So you can see this coming up again and again. So if you have trouble to find the bands for R, then you just need to do more practice here. Okay, so how are we going to find the size of this circle here? Is from the intersection, right? When you do the projection, you can see the largest part is when the plane is equal 6 intersect with the paraboloid. Okay, so that would be the intersection when we do the projection. Okay, so we're set them equal to each other, and we're going to get 2 equal to 2x squared plus 2y squared. So x squared plus y squared equal to 1. So this is a unit circle, r equal 1. Okay. So R is from 0 to 1, and theta is from its only first quadrant, so up to power 2 here. And now this is 8 minus 2r squared minus 6. The upper surface minus the lower surface. dA, do not forget the Jacobian, R, dr, d theta. Is that good? So this is how we set it up, okay? This is how we use the double integral. So for those of you prefer the triple integral, then you're going to set up this way. So the bands for R and theta are the same. Now z is from the plane until it touched the paraboloid. Do you see that? You're going to draw the direction, a line in the z direction. The lower band is z equals 6 until it touched the paraboloid, which is 8 minus 2r squared. Okay, so you can either use the double integral or the triple integral here. For this question, it didn't mention it, so either way will be fine. Okay, they are equivalent. Okay, and the anyone need me to evaluate this integral here? This is not that bad. This is just a polynomial, right? Okay, so here you're going to get 2 minus 2r squared times r dr d theta. So you're going to get 2r minus 2r cubed. So you're going to get r squared minus 1/2 r to the power 4, 0 to 1. We are integrating the inner part here, okay? Inner part. So plug in, you're going to get 1/2. 1/2 times 0 to power 2, that's power 2. So you're going to get power 4. Is that good? So the final answer is power 4. That's the volume. Okay, someone is asking here, why we choose the region above z equals 6, not below. Here it says the volume of the solid is bounded by these two. So if you choose below, you can see because this is keep going down, then the volume will be infinity. Do you see that? It need to be bounded. Yes, exactly. It need to be bounded. Okay. But if you choose below, it's not bounded. It just keep going down. The volume is infinity. But yeah, we still choose the first quadrant, but still infinity because it keep going down. Okay. All right. So when we say bounded, then it's between the two surfaces. When we say bounded. Okay. When we say bounded, that means it's between those two. Between those two, that would be above z equals 6. All right. All right. And now let's look at 15. Question 15. This integral given here, we want to change a variable x equal to u plus v, y equal to 2u here. So let's look at the region we have here. And y is between 0 and 4. And x is from y over 2 to x equal to y over 2 plus 1. So you can see those are the two parallel lines here, as you can see. So let's draw the region first. Figure out the region first. Y equal to 2x. This is y equal to 2x through the origin. Okay. And x equal to y over 2. And x equal to y over 2 plus 1. So that's another line here. They are parallel. Okay. So this is x equal to y over 2. This is x equal to y over 2 plus 1. And y is between 0 and 4. So this is the region we consider here. Okay, so this is the region R. Okay, is a parallelogram. And now we're going to do the change of variable x equal to u plus v, y equal to 2v here. So we want to find the corresponding region on the UV plane. Okay, so you can see for so for this parallelogram, there's 4 line segment. Okay, this is y equals 0, and we have y equals 4, and we have x equal to y over 2, and we have x equal to y over 2 plus 1. Okay, y over 2 plus 1. Now we're going to write the equation on the UV plane. Okay, so this is the change of variable given, x equal to u plus v, y equal to 2v. Okay, so let's plug in. Y equal to 2v, theta equal to 0. So we have v equals 0. Y equal to 4, so y equal to 2v, so v equal to 2. The next line, x equal to y over 2, x equal to u plus v, y over 2 is v, right? So you can see v is canceled from both sides, so you have u equals 0. And the next one, x equal to y over 2 plus 1, x equal to u plus v. And y over 2 is v plus 1. So again, v is canceled from both sides, you have u equal to 1. So those 4 lines on the xy plane present those 4 lines on the UV plane. So u is between 0 and 1, u is between 0 and 1, and v is between 0 and 2. So you can see we got a nice region here, rectangular region S on the UV plane. Is that good? Okay, so this is the first step. If the given region R, you need to find the corresponding region on the UV plane. And now you're going to calculate the Jacobian. Okay, so this is the first step. You find the corresponding region on the UV plane. And next, you're going to calculate the Jacobian. The Jacobian is from XY to UV. So we're going to set up the 2 by 2 determinant here. So we'll have 1, 1 and 0, 2. So calculate the 2 by 2 determinant, you have 2 minus 0. So the Jacobian is 2. Okay. And the third step, you're going to write this integral. Let me copy that down because it doesn't show on camera here. So let me copy down the integral. So this is the given integral. Now we are going to convert the integral to du dv here. Okay, so to write as du dv, u, as you can see, is from 0 to 1. V is from 0 to 2. Okay, and now for this function here, we have 2x minus y over 2. So we're going to use the change of variable. Do you see that? X equal u plus v, y equal 2v. We're going to plug in. Okay, so x equal to u plus v, 2 times u plus v minus y is 2v, whole thing divided by 2. Is that good? This use the given change of variable here, x equal to u plus v, y equal to 2v here. So as you can see here, the numerator 2v is canceled. We only left with 2u on the top. 2u over 2, we'll have just u here. Is that good? Did I make any mistake here? Yeah, do not forget, you can see here, we calculate Jacobian and we need to use it, right? Okay, so the Jacobian, when you do the change of variable, you need to put the absolute value of Jacobian, but the Jacobian here is positive, so we don't need the absolute value here. So the integrand here would be 2u, 2 times u, okay? 2u here, okay? And this is not bad to find the integral here, okay? And you'll have 0 to 2 dv, 0, 1, 2u du. So we'll have, this is 2 times this is u squared from 0 to 1, that's 1. So the final answer is 2 here. Is that good? All right. The answer is 2. So this is question 15. Next. 16. Question 16 is the region above the circular disk bounded by the circle r equal to 2 sine theta. Okay, so this circle r equal to 2 sine theta, this circle is where is the circle? Where is the circle? On the y-axis, okay, it's on the y-axis. So the disk is on the y-axis here. It's a circle, okay? It's on the y-axis. So this is r equal to 2 sine theta. Above the plane z equal to 4 minus y. So there's a plane going this way, okay? So you can see would be something like this. So this is the region E. The top is the plane z equal to 4 minus y. And the volume can be written in this way in the cylindrical coordinate. So now when we project the whole thing onto the XY plane, it's just a circle, right? This is a circle, r equal to 2 sine theta. Therefore, to find the bands for r and theta, you can see r is from 0 until it touch the circle, r equal to 2 sine theta. So b equal to 2 sine theta here. And the angle theta, can anyone tell me the angle theta is from?
0 to pi.
Yes, this is theta equals 0, and this is pi over 2 on the top. So from 0 to pi over 2, we got half a circle, and then go around. This is theta equal pi, okay? Theta equal pi here. Now to figure out the bands for z, we're going to look at the solid here. It's from the xy plane until it touched the plane, z equal to 4 minus y. So it's from 0 to 4 minus y, but now we are in the cylindrical coordinate. So we're going to write c equal to 4 minus r sine theta. So now we have the bands for the cylindrical coordinate. Is that good? This is question 16. And let's look at question 17. Question 17, we want to find the volume, and here is using the double integral. So this is the upper surface minus the lower surface. Do you see that? The upper surface minus the lower surface dA. Okay, so that gives us the volume. The upper surface is z equals 3, which is the horizontal plane. And the lower surface is z equal to the square root of x squared plus y squared. So this is the cone. So we have something like this. A cone on the bottom here. On the top is the plane z equals 3. Okay, the upper surface minus the lower surface. And now look at the bands we have here. When we do the projection onto the xy plane, what do we have? Do we get the entire circle or not? Based on the bands we have here. X is from -3 to 3, y is from 0 to square root of 9 minus x squared. So what do we have here?
A semicircle of radius 3.
Yes, a semicircle, but which side? Top, bottom, left, or right?
Top.
Yes, the top. Okay, so it's the top half of the semicircle here. Okay, so we do need to know that. Okay, if the right side, then the angle theta is from minus pi over 2 to pi over 2. So the angle theta would be different. Okay, so in this case, theta is from 0 to pi. So theta from 0 to pi, we can ignore this 2, right? Because this 2, theta is from 0 to 2 pi, that consider the entire circle. We only need half of the circle from 0 to pi. So we still have 3 choices to consider here. And next, we're going to consider, let's look at row here, okay? So to determine row, you're going to draw a ray through the region. You can see it's starting from the origin, is from 0 until it touched the plane z equals 3. So how are we going to write z equals 3 in spherical coordinate? We did that earlier, remember? Z is rho cosine phi, right? And set equal to 3. So rho equal to 3 secant phi. So the bounds for rho is from 0 to 3 secant phi. So that gives us the answer right here. This one. Rho is from 3 to, from 0 to 3 secant phi. And let's check the angle phi. The angle phi starting from the positive z-axis, which is phi equal to 0, getting larger and larger until it touched the edge of the cone, and z equals square root of x squared plus y squared. That gives us the equation phi equal pi over 4. So that's the bounds for phi. Okay, is that good? Can we always assume that if it's a cone, so we always have phi equal pi over 4? Can we? No, only when z equal to square root of x squared plus y squared. Okay, it's not always pi over 4. Okay, but whenever you have, this is, I would say probably more than half of the time we see this type of cone, z equal to square root of x squared plus y squared. Then we have phi equal to pi over 4. Okay, if there's a some other coefficient here, then the angle would be different. Okay, the angle would be different. Okay. All right. Question 18. Now we want to convert this to in rectangular coordinate here. So you can see r dr theta that give us dy dx. Now let's draw the region here. Theta is from 0 to power 4, and r is from 0 to r equal to secant theta. So first, look at this equation, r equals secant theta. What's r equal to secant theta? Secant we can write as 1 over cosine, right? So if we multiply cosine on both sides, we're going to get r cosine theta equal 1. And what's r cosine theta? X equal 1. So this is x equal 1. R is from 0 until it touch the vertical line, x equal 1. And what's theta equal pi over 4? Can anyone tell me? Theta equal pi over 4, that present the line y equal x. Because y equal x, that's when tangent theta equal 1, right? Tangent theta equal 1, that's when theta equal pi over 4. Okay, so this is the region we consider here. This is the region we consider because you can see when we draw a ray here, r is from 0 until it touch equal to secant theta, which is the vertical line x equal 1. And the angle theta is from 0 until it touched the line y equal x, that's pi over 4. So this is the region we have. Okay, this is the region we have. Now we're going to write this in the rectangular coordinate, and we want to do dy first. When we do dy first, we're going to draw a line in the y direction. Y is from 0 until it touched the line y equal to x. Okay, so on the test, I will prefer you to write this on the scratch paper and then enter the bands corresponding to what you have on the scratch paper, because it happened in the past. We have students, they have those two flipped when they enter it. If you flip the bands, like the dy dx, but you write the bands for x first here, then you won't get any credit on the test. Okay, so you probably want to write this on the paper first and then enter the corresponding what do you have on the paper. You enter it on canvas, okay? And X is from 0 to 1. So 0 to 1, okay? So once you have this on the paper, then A to B, so it's 0, 1, C to D is 0, X. So this way, you will get the order correctly, okay? Is that good? So this is question 18. And 19, we want to change the order for triple integral here. Now, this is doing the z first. Z is from 0 to the plane z equal to 1 minus y. Z equals 0 is the xy plane, okay? And z equal to 1 minus y is the plane cut in the, let me draw a picture here. It's cutting it this way, okay? You pass it through the those two intercept here, okay? 0, 1, 0, 0, 0, 1. And now when we do the projection onto the xy plane, dy dx, we have x is between 0 and 1, and y is from square root x to y equal 1. Y equal to square root x is like this, y equals square root x to y equal 1. This is y equal 1, okay? And y is from square root x to 1, so it's this direction. So this is the region we have, okay? So based on this two together, are you able to draw the solid? So you can see that when we project the whole thing onto the xy plane, this is the region D we have, okay? So this is the region D we have. So on the xy plane, we have something like this. That's the square root x. This is y equal to square root x, and this is the region D. And now the z direction, in the z direction is from the xy plane until it touch the plane this way. So the plane is passing through the intercept 0, 1, 0, 0, 0, 1, okay? And y equal to square root x on the plane is a curve like this, but in 3D is a cylinder going on the z direction. So when the plane and this cylinder meet, will be a curve like this. This is the intersection. So this curve is the intersection of the cylinder and the plane. So this one is the plane, z equal to 1 minus y. And this side here, this is the cylinder, y equal to square root x. So this is the solid we consider here. Now we're going to change the order of integration. We want to do dx first. So to do dx first, you're going to draw a, inside the region, you're going to draw a line in the x direction. Okay, in the x direction. So it's from the back, which is the yz plane. Okay, so that's 0. Until it touch the cylinder, y equal to square root x. So that's x equal to y squared. Okay, well, x equal to y squared. So that gives us the bands for x. So to look for the triple integral, when you want to integrate, when you want to integrate, it doesn't matter dz first or dx first, you're going to look at the solid. When you do dz first, you're going to draw a line in the z direction. You can see z is from 0 until it touch the plane, z equal 1 minus y. But when you want to do dx first, you're going to draw a line in the x direction. This is the x direction. So it's from the back, the yz plane, until it touch this cylinder here, x equal to y squared. Now we're going to project the whole thing onto the yz plane. When we project the whole thing onto the yz plane, you're going to get this triangular region enclosed by z equal to 1 minus y and the coordinate axis here, okay? So this is the projection on the yz plane, okay? And we want to do dz first. So we're going to draw a line in the z direction. In the z direction, as you can see, it starts from 0 until it touches the line, 1 minus y. So it's from 0 to 1 minus y. That's the direction for z. And y is between two lines, 0 and 1. 0 and 1. So now we have find all the bands here. Okay, so again, write down this on the paper. And now when you enter your answer, you're going to enter from the outside one, starting from the outside, the lower band to the upper band. So you have 0 to 1, and then 0 to 1 minus y, and then 0 to y squared. Okay, because it happened before. We have students, they have those two switched. Okay, so it's better to write down on the paper first, so you won't confuse about the order when you enter it on Canvas. Okay, so this is question 19. All right, and next 20. 20, we want to do the change of variable here, and we have doing this so many times already. The region enclosed by the ellipsoid. So the change of variable we're going to make here, we want to make a unisphere, u squared plus v squared plus w equal to 1. So we're going to reshape the region, okay, in the x, y direction to make it a unisphere. So can anyone tell me how we're going to choose x, y, and z, the change of variable? So you can see in order to get u squared, we need to get rid of the 4 here. So we're going to make x equal to 2u, right? If x equal to 2u, then 4 is canceled when you square it, okay? And y equal to 3v, z equal to w. So this is the change of variable we're going to use to make a unisphere here, okay? So once we have this, so this, let's call this is the region enclosed by the ellipsoid, and this is the region enclosed by the unisphere, okay? S. So this is the first step, which choose the change of variable. The second step, we're going to calculate the Jacobian. It's from xyz to uvw. So you save up, we have 200,030,001. So the Jacobian here is just 6, okay? So this is the Jacobian. To find the volume, then we'll have the triple integral over the region E 1 dv. And now we're going to convert using the change of variable here to the UVW space, okay? So it's over the unisphere, okay? The region enclosed by the unisphere. So we need to multiply by the absolute value of the Jacobian, which is 6. And now we have du, dv, dw here, okay? So this is how we do the change of variable, okay? And now you can take out the constant 6 outside the integral. And the triple integral here, because the integral is 1, then this means the volume of the unit ball, which is given here, 4 pi over 3. So we can just put that in, 4 pi over 3 here. So that's 8 pi. That's the final answer. Is that good? The answer is 8 pi. And this is the last question on the practice exam. And let me start recording here.